So we got the recording going. So now we're rolling. I'm going to put my student view on and let's see what we got here as far as what do we have coming up in our class. I always like to spend a minute and look at what is due and what's coming up. So the best place to do that, of course, is to look at your class announcements, right? Always scroll through those announcements to make sure you haven't missed anything, make sure you're up to speed on stuff. So we have our class 6 video was posted, some other video links there. I'm going to go then to our course calendar and see what's coming up. So here we are on the 11th. Tomorrow, what's up? Charging and starting system diagnostics. Now, we were talking about this last week, and we're going to go through it again today. In fact, I'll click on it and just kind of hash this out one more time. Okay, so I have some links here to the battery presentation, the charging diagnostics presentation. The idea is that you record a short video of you testing your battery's voltage. And, you know, to kind of help us illustrate some of this stuff, not only do I have a video clip, but I'm going to pick on CDX here real quick. So what I love about this program is it has some nice animations. So I'm going to go to this chapter 54 and I'm going to pick on some of those animations under the media gallery, guys. And so let's start with this starting system testing. Okay, because it shows us a nice cutaway of a starter. And it's got the meter already hooked up to the starter here. Now, I would say this animation's not perfect, but it's pretty good and it gives us some stuff to talk about, okay? The test that you're going to do in that worksheet, basically, if I go back to our if I go back to Canvas, it's going to ask us to hook up to the battery and measure the battery's state of charge. Then we're going to do an available voltage test. And then we're going to start up the car and allow it to run. And now we're going to do the voltage output test or voltage regulation. Okay, so let me take those terms and let's put those on our CDX page real fast. Okay, so the first thing we would do is we would hook up to our battery and measure the state of charge. So I can get my zoom controls working. There we go. Get our text tool going. So number one, we're going to do SOC. We're going to measure the state of charge. Number two is we're going to measure available voltage. Number three, we are going to then look at our, I'm going to say voltage. I'm going to say charging voltage. Or voltage regulation. Okay. So in this graphic, we're hooked up to the battery. And ideally you would have your, your alligator clip so you don't have to hold the leads on there so that then you could take your phone and do a video with your phone, right? But you're going to hook it up to the battery and you're going to see, okay, what is the state of charge of this battery? So let me go over this thing real quick. If we hooked up to this battery and its state of charge was 100%, we should measure 12.6 volts, right? So that's what our meter should say with the car off. Notice that it's off right now, 12.6. Now, if I walked up to it and I hooked up my voltmeter and let's say it said 12.9 volts. What would I think is going on there, and what should I do at that point? What do you guys think? Who's out there? What do you guys think? I'm hooked up to the battery. The car, you know, it's not running, right? The key is off. I'm measuring 12.9 volts. What do you guys think? Why is it
off the surface charge?
Yep, it's got the surface charge, right? So what I would do is I'll put like a sub thing to do is I'm going to say, you know, 1A would be let's make this a little bit bigger. Headlights on 30 seconds. Okay. And what that will do is suck off the surface charge. And then B would be, okay, after I've turned the headlights on, wait 15 seconds and then look at it. Okay, so if I walked up to this thing and the voltage was reading a lot higher, it was reading here at, you know, 12.9, maybe it's sitting here at 13.1 volts or something, right? I go, oh, well, maybe there's surface charge on there. I'm going to turn the headlights on for 30 seconds, shut them off, wait 15 seconds, and see what the voltage is now. And that voltage should stabilize out. It should drop down, and then after you waited 15 seconds, it should stabilize right out at 12.6. And if it does, that tells you that the battery is fully charged. If it drops down to 12.5, well, now it's at 90%. 12.4, now it's down to 80%, right? So use that chart in the battery diagnostics presentation to kind of figure that out. And if you're not sure, right, you could always just, you know, go to Google. And if we go to 12 volt auto lead acid chart, we should be able to pull one up here. Let's see. That's for an AGM. AGM is going to be a little bit different. There we go. Here's one that's has AGM and wet cell lead acid, right? So notice AGMs will sit with a little bit higher charge. Wet cell lead acid, your typical battery, 12.6, 12.5, 12.42 is 80%, right? I mean, they're pretty similar. It's not a linear scale, okay? So that's the first thing that tells you about that battery's state of charge. Okay, so we've done essentially that first thing. I'm going to cross him off the list, right? Then what I would do is I'd crank over the car and I get it running. Or I'm sorry, first I'd crank over the car and eventually it's going to get running. But first I'm going to crank over the car and I'm going to see what the battery voltage drops to. So this available voltage test, think of this is like, this is what what voltage is available to everything on your car while you're cranking over your engine, okay? Now remember, with this available voltage test, what I want now, oops, that's not what I wanted to do. What I want to do now is I want the available voltage to be, I'll change colors here. I want it to be above 10.5 volts cranking. Now, why 10.5 volts? Well, what you guys can't see in this picture is that there's other circuits hooked up to the battery, right? In fact, one of the things that's hooked up to this battery that's really responsible for running your car these days is going to be your computer or powertrain control module. And that PCM, he needs to make all kinds of decisions on when to fire the spark plugs, when to turn on the fuel injectors and for how long, and to run the fuel pump. So he has to make these important decisions. And what happens is if the voltage is too far below 10 and a half, he starts making the wrong decisions, and it may not allow the car to start. So I've had several cars where they did crank over, but they cranked kind of slowly. And when I measured the voltage, he was below 10 and a half. And just by fixing that issue, whether I put a jump box on there, I put a new battery in the car or whatever, by getting that voltage above 10 and a half volts, that took care of that hard starting problem. Okay, because remember that this PCM, he's also over here, he's hooked to this battery. So if the battery's voltage is dropping down to, well, let's crank over this mock-up here. If it's cranking down to 9.8 volts, that can be enough to throw off the PCM from his calculations, and now the car becomes hard to start, okay? The computer might still work, but it might go into some type of limited strategy where maybe it commands more fuel injector on time. And so now maybe the car is more likely to flood out, or maybe the spark is not at the same point. It could go into some type of alternative strategy due to low voltage, and that alone can make the car hard to start. So when I say available voltage, it's the available voltage, think to like the computer and all the other circuits on the car while you're cranking over the engine. And we really want it above 10 and a half volts, especially for a car that is computer controlled, right? If it's your 1965 Chevy, carbureted, no computers in the car, well, that's one thing. But if it's a modern car that's from the, late 80s, 90s, 2000s, that's a totally different deal. And he's going to want to see good voltage there. So what I would say is with this little graphic that they have here on CDX, I don't necessarily agree with this all the way. What they are showing is that, hey, as the temperature outside drops, the available voltage will tend to drop with it, right? They're also cranking this thing over for a full 15 seconds. So like at the end of 15 seconds, they're saying be above 10 volts if it's 90 degrees outside. Why do you guys think that this thing has this temperature scale here so that if the temperature is dropping, it's like they're giving the battery more leeway, like they're allowing the voltage to go lower? Why do you think they're doing that? What do you think?
Well, the cold causes the whole process of the battery to slow down.
Yeah, Brad, that's exactly right, right? My analogy is that batteries are like lizards. When they're hot, right, they're running fast, right? But when they're cold, they're slow and sluggish. So that we tend to give batteries more slack when they're cold. The reality is, though, I don't care about that. If the car doesn't start, it's not cutting it for me. So I'm not super happy with this chart because I can tell you from real world experience, when you start dropping below 10 and a half volts, you're now in a borderline territory where the computer might be able to start the car or it might not. And so I get real suspect of that. And so what I would usually do, if I have a jumper battery available, I'll throw it on there. And so I'm giving it like extra battery capacity, and then I measure the voltage. And if the voltage stays above 10 and a half volts, and now the thing fires up really easily, well, I know, okay, that's my issue here, okay? So that being said, let's say we do have a car that the car it's hard to start. I hook up my voltmeter. I'm getting 9.8 volts. It does crank over, but it cranks over maybe a little slowly. So I got a little bit of a slow crank. It's hard to start. This is down to 9.8 volts. Then we have to ask ourselves, well, what would cause that, right? And I think last week I told you guys that my Cadillac story, right? You end up with a couple scenarios. Either the battery does not have enough capacity, right? Remember that a starter motor, when I turn this guy over here to crank, a lot of stuff just happened, okay? When I turn to crank here, current flowed from the positive battery cable through the ignition switch, through the control side of the relay. The relay made a magnetic field, and I just energized that relay, right? That magnetic field then closed the relay contacts. Now, more current can now flow through the ignition, up to the ignition switch, through this fuse, through terminal 30, to terminal 87, and now can flow into the solenoid. Now, because current flowed into the solenoid, I want you to watch the solenoid. What it does is it engages. It's a big electromagnet. So not only does it engage the solenoid, that kicks out the starter drive, but it also bridges the contacts here. So a solenoid is really, it engages the starter and it acts as a heavy duty relay or switch at the same time. So if I turn this thing on again, what's happened is the solenoid has energized. It's bridging these contacts inside here, and it kicked out the starter drive to engage him with the flywheel, right? So more current flowed through the switch circuit of the relay, through the starter solenoid, ultimately to ground, engaged the starter solenoid, and kicked out the starter drive gear. That now allows a large amount of current in the range of 100 to 200 amps to go through these contacts that are now closed into the actual armature windings of the starter motor and to crank him over, right? So a lot happened when I turned that key to crank. So the moral of the story is we're at this point in time, we might be flowing, anywhere from 100 to 200 amps, maybe even more if it's a big engine, a lot of compression. So let's say I'm flowing 180 amps out of this battery at this point, cranking over this car, right? What the available voltage test is doing is as those 180 amps are flowing out, can the battery maintain adequate voltage, right? Adequate electrical pressure under that situation. Well, if I have a battery that is, 4, 5, maybe, 6 years old or more, remember that batteries do age out. They're taking a chemical reaction and using that to make electricity, right? And as they get older, they get less and less active. So not only do you have the temperature working against you, you have the age of the battery. Okay. We talked about batteries sulfating last week. I mean, so you have all these things working against you. So if I had the situation where I had a slow crank, my available voltage was low, below 10.5 as I cranked over the engine, and it was kind of hard to start, like it didn't want to start properly, I'd be really suspect of the battery if it was older. If it was, 4 or 5 years old, I'd be like, yeah, I probably need a battery. Now, we don't just kill stuff with one diagnostic test alone, right? So what could I do at this point? Well, maybe I take that, I drive my car, if I get it started, I drive over to the auto parts store and have them do that battery test with their Midtronics tester or something like that. So maybe I get another type of tester on there. Oops, I don't want to go away from that because I got too much stuff drawn on here right now. So maybe I follow up with another test. Maybe if I crank the engine over for a while and now the battery voltage is low, maybe I could then jump into a 3-minute charge test. But I would do a couple other tests to determine if the battery really is good or bad. But I would be highly suspect of the battery just being just too old to supply adequate voltage while cranking if I had a slow crank and the available voltage was low. Okay. Now, let's say I have a brand new battery in there. Or maybe I took this thing to the auto parts store, they tested it and they said, yeah, the battery's at, 40% state of health, and I threw a new one in there. So I crossed the battery off my list of possibilities, right? So the battery we're going to say is okay at this point, but guess what? Available voltage is still lower than what I would like. The car is kind of a slow crank and it is hard to start, right? Well, basically at this point, the assumption would be, well, if the battery is okay, I'm probably pulling too many amps out of this thing. And even the best battery, if I'm trying to pull a zillion amps out of it, it's not going to be able to maintain a good voltage level with that many amps going through it. So I probably got to be pulling way too many amps. So maybe I'm pulling like 300 amps or something. Without a way to measure the amps themselves, without some type of an amp clamp on your meter or something, you're not going to know what that is, right? But you know that there's really only a couple possibilities that would cause it to pull a bunch of amps, right? So one possibility is that the starter motor is shorted. So I could have a shorted starter inside the car. So that would be one possibility. My other possibility would be that I have a tight engine, right? And so I could eliminate that with some hand tools. Like if I physically got a big, 1/2-inch drive ratchet on there and physically turn the motor over, and it's, I should be, it won't be super easy to turn, but I should be able with a 1/2-inch drive ratchet to crank the engine over by hand and feel the compression, but it should be able to move smoothly. And so I can manually feel if I have a tight engine or not by cranking the engine over by hand, right? So I can eliminate this possibility. So if the engine is not tight, the battery's new, my available voltage is low, then I come down to, okay, I have to have a starter motor that's pulling too many amps. Now, remember that starter motors themselves are electric motors, and they have to apply by those rules. So now I'm going to clear out all my scribbles. Okay. So far we've done state of charge, and we're doing available voltage. And, our situation was the available voltage was lower than what we'd like to see. And the car is hard to start because what we'd really like to see is stuff above 10.5, right? So I'm going to clear out all these drawings, and I'm going to go back to this. And let's just go to DC motors. And it's thinking about opening it. Okay, so there is a cool little animation of a DC motor. It's got one single loop of the armature, which is the piece in the center that spins. And what I want to point out to you guys is, how an electric motor works, it's all off of magnetism. Remember that whenever I'm flowing electricity through wires, I'm creating electromagnetic fields around those wires. And if I want that magnetic field to be stronger, what I would do is I'd wrap up the wires many, many times, and that's going to increase the strength of the magnetic field, right? We also know by, if you've ever played with magnets, right, that opposite magnets attract and alike magnetic poles repel, right? So two norths will repel against each other, and a north will be attracted to a south. That's how the motor works on the inside. You have a mix of magnetic forces repelling each other and being attracted to each other. And what we're constantly doing is switching the polarity around as this thing spins by means of the commutator and the brushes that ride on it. So I'm getting to a couple scenarios of motor failures. One scenario is that as the motor ages, its brushes wear down. In fact, the starter motor is not made to run nonstop constantly. It's a brushed motor. And that means that I have 100 amps or more flowing through those brushes. And so that's why when we crank over our engine, we're not supposed to crank it over for more than 15 seconds because that starts to overheat the starter. And, after 50, 60, 100,000 miles, by that point, there's been so many starts that the brushes have worn down to little nubs, and they usually start to increase their resistance. So you might have a car that's a slow crank that you have too much resistance in the starter motor, and that's why it's a slow crank. But that's not our scenario, because remember, if resistance is up, the current flow is going to go down. We were saying in our made-up scenario that the current flow was high. So what could cause that? Well, again, if you crank over the engine, you know, over time, this whole thing gets nice and hot. And remember, it's not just one loop of wire in here. In fact, it's many loops of wire, so many that we wind all those together in the form of an armature. Okay. So with that armature, if I go back to this picture here, what you can see is not only does the current flow through the armature, which is the part in the center that spins around, right? Not only does the current come in here and end up, you know, getting into the brushes and flowing through the windings of the armature through the commutator there. So you can see it flows into this brush, moves around, gets to ground through that brush, right? Because the case of this thing is connected to ground. But if you're paying attention here, you notice that it goes through the starter solenoid. It first goes through the field coil windings on the outside. So, you know, it's moving around all over the place. What I'm getting to is that there is a lot of turns or coils of wire in a motor. And what happens is if you crank it, just over time, heat and age, the windings inside the motor can begin to short together. And when these guys begin to short together, of course, think of short. Well, that means the resistance is going to go down. And so the current flow, the amps, is going to go up, right? So getting back to our starter motor graphic being at 9 volts, well, it could be that if the battery is good, that it's just pulling way too many amps because the starter motor itself is shorting out internally. Okay. So you can see them fail, you know, a couple of ways. Sometimes they fail and it's a high resistance issue because the brushes are just worn down to little nubs. And so it's a slow crank, but the battery voltage, instead of being down here at 9, it's maybe up at 11 and it's a slow crank. And you go, well, why is it a slow crank? It's got plenty of volts. Because it's not able to move the amps through the starter because the resistance is high, right? Usually due to worn brushes. The other end of the spectrum is this. The voltage is too low because it's pulling way too many amps because the starter motor is starting to short out internally, right? So if the physical engine in the car isn't tight or hard to turn, then it's got to be the starter motor shorting out. So this available voltage test can really tell you a lot of information when you start to break it down and think about it. So, you know, how hard was the hookup? Well, I hooked up my meter, maybe used a couple alligator clips, cranked over the car and looked at it, right? But in that 15 seconds, I learned a lot of information about what's the battery state of charge. That gives me a little bit of indication of its health and what's it able to do as far as available voltage. That again tells me some information about the battery and some information about the starter motor. I do have to do some other tests to really isolate exactly what's going on, but it definitely allows me to pick a direction for where I'm going. Okay. So to carry this out, remember that the third part of the test was to actually let the car start up. Number 3 was, you know, the car starts and we measure our charging voltage, or I'm going to say voltage regulation. Okay. Well, for that, what I'm going to do is I'm going to change this graphic because I'm going to move over to the one that is a charging system. So we'll clear that out of there. We'll move this over here. We got that down. We got that down. And we're going to go to charging system testing. Okay, and we'll look at some other charging circuits here in a minute. What I do want to say, though, that I think a lot of people don't realize is that your charging system works in a couple of ways. Like I'm going to click the thing that says run an engine, run the engine. All right. Notice it starts spinning. Okay. You also notice that it's got a couple of wires here that are connected to the battery. Well, you've probably heard the expression, it takes money to make money. And, you know, that's a pretty true saying if you think about it. But in this case, our true saying here is it takes power to make power, in that it's going to take some current from the battery to make the alternator then charge up and charge the battery more. So let me turn this thing off, and then I'll turn the ignition on. Okay, so I'm off right now, nothing's going on, right? What you're going to notice right now is, hey, the ignition switch right here, he's open, right? So now I'm going to turn the ignition switch on, and now what you should realize is, hey, the warning lamp just turned on, okay? That's the lamp that a lot of times looks like a little picture of a battery on your dash, okay? So the warning light turned on, key on, engine off, okay? This is where I'm at. Well, what's happening right now? It takes power to make power. So current is flowing from the positive battery post through your ignition switch, through maybe some fuses and stuff, through the warning light on your dash, but just in case that warning light burned out, there's also a parallel branch in there, okay? And ultimately, it gets into the voltage regulator inside the alternator. Most alternators built in the last 50 years will have an internal voltage regulator. Unless you're working on some car that's like, in the 60s or maybe early 70s, it might have an external voltage regulator, but most stuff will either have an internal voltage regulator, or new cars, the computer will control the voltage. But anyways, it will go inside the alternator, go through the regulator. And remember how we were talking about how there was a couple brushes to get the power in and out of the commutator and armature of a starter motor? Well, there's a couple of brushes and slip rings here, and that gets this current into and out of the rotor of the alternator. So what it does is it gets in there and ultimately then comes out, goes to ground. And what it's doing is it's making a strong magnetic field. This part inside the middle of the alternator, it's called the rotor, and it rotates. What causes it to rotate? Well, there's a belt driven off your engine, right? So what I think a lot of people don't realize is, first, your charging system needs power from the battery to first start to build a magnetic field. So it takes power to make power. So it needs power from the battery, but it also needs horsepower from your engine. Because what we're going to do is we're going to take that power from the battery coming in through the warning light to charge this thing up and make a magnetic field. Then the engine starts running and starts spinning the alternator. Now, with some horsepower being applied, now I have a changing magnetic field that will then in turn generate a lot more power, a lot more than what I'm taking in. I might take in, a few amps. I might take in maybe 5 amps, 10 amps maximum, but I'm going to pull out, maybe up to 100 amps, right? Whatever this thing's rated at. So I'm going to have many times the amount of current flowing out of this thing based on the small amount of current that went into it. And of course, once it starts to generate electricity, he can essentially feed himself. So it takes initially, before the car starts up, it takes some power from the battery to get it going. So what that does mean is, let's say you had a battery in your car that was completely dead. I mean, it was dead as a doornail, 0 volts, okay? If you went to push start that car, you'd never be able to get it started, because you at least need some voltage from the battery to flow through this circuit to make the magnetic field. So then once you start spinning it and you push start it, you get it running, it can then generate more electricity, right? Generate more power and feed itself, right? So if your battery's 100% dead, you're stuck, you're done. So hopefully that makes sense. Now, in this graphic, what the guys at CDX say is they say, okay, well, regulated voltage should be 14.2 to 14.6 volts. You know, and that's pretty close. They're saying this alternator in their example is supposed to have a max output of 85 amps at 2200 RPM. Like that's the spec maybe that they looked up on All Data or Mitchell on Demand, Shopkey Pro, something like that. What I will say is that generally speaking, this regulated voltage is going to vary. When I'm here at, one thing you'll notice is I'm down here, I'm at 800 RPM right now. You can see it's spinning kind of slow. If I spin it faster, now I'm at 2500 RPM. Well, that's when the alternator is going to be more efficient because it's able to take more mechanical energy from our engine, right? And so that's when I could get my maximum output out of the alternator. So if this alternator was really rated at 85 amps, it's not going to say 85 amps at 600 RPM. It's 85 amps at 2200. So I have to spin it up to get its maximum output. So I start the car, I get it running, I go ahead and rev it up. And when I rev it up, what I like to see is not 14.2 to 14.6. I have a little wider range because I have found that cars really do vary around more than that. What I'm looking for is 13.8 to 14.8 volts, okay? And you might see some cars with AGM batteries and cars with a lot of electrical loads on them. They might run those suckers in cold weather up as high as 15.2 for some stuff. But most stuff, 13.8 to 14.8, that's a pretty good range of where you're going to find stuff. Now, again, my range is a little wider than what the guys in CDX said. But what I find is that, you know, as cars get more modern and they're trying to get more life out of stuff, one of the things they like to do is try to regulate how much the charging system charges the battery based on what they think the battery's temperature is. So a lot of times they'll use either temperature circuits like that are built into the computer, or they might use the intake air temperature. They might even have a separate battery temperature sensor somewhere hidden on the car. But they're going to infer what the battery's temperature is so that they don't overcharge the battery when it's really hot outside. So a modern charging system to prevent us from boiling the electrolyte out of the battery, and I showed you some pictures maybe last week or the week before, we had like wet battery tops and stuff. A more modern charging system will usually be computer controlled, but even some of the ones that weren't computer controlled, that they had a regulator inside the alternator, sometimes the regulator would have a little variable temp sensor in there. So from whatever temperature the alternator was, it could then infer what the battery's temperature was going to be. And as it got hotter, what we would see is the voltage regulation would move down. When it was colder outside, it could move the voltage regulation up without fear of boiling the electrolyte out of the battery. Well, that's probably more information than you guys needed to know. I guess we could boil it down to is, what am I looking for? 13.8 to 14.8. So let's pull this thing full circle. This worksheet that's, this little lab video that's due. What are you looking for? We'll get rid of all these crazy scribbles here. We're looking for you to hook up your voltmeter just like what's pictured on the screen there. Measure what the state of charge is. This battery in this picture looks a little low. It's sitting at 12.18, right? That's pretty low. So look at the state of charge, crank over the car, see what the available voltage is. What does the voltage drop down to? I really want it to be 10.5 or above, okay? To catch all that on my screen, unless I have a meter with a min-max feature or something, if I just have this little cheapo meter like what's in that picture, and I have one right here, this is why recording it with my cell phone's nice, because not only do I need to do that for this activity anyways, right? But it allows me to catch the numbers because they might flash on the screen so fast. I'll see them and then I can't remember what that said. So I, do this, I get the recording going. I see what the voltage drops down to. I want it to be above 10.5. And then once the car starts, I expect the voltage to jump up. And I expect it to jump up to somewhere above 13. Once it's running, rev up the engine a little bit, right? Rev it up to what feels like 2000 RPM or so. So you know the alternator is spinning adequately fast enough, and see, is that voltage between 13.8 and 14.8 volts? And if it is, that tells you that everything's looking pretty decent with this thing right now, right? So if the state of charge is, 12.5 something to 12.6, that's looking like it's a pretty charged battery. So that's good. If the voltage stays above 10.5 while cranking, the available voltage just looks good. So that would tell you the battery, starter, working good together, good cranking speed. You're also listening to that. And you fire it up and it's 13.8 to 14.8. Again, everything looks good. So from this one test that you can do in a total time of like 15 to 30 seconds, maybe, you can learn a lot about the general health of your major electrical systems on your car, battery, starter, alternator. That's what this activity is all about. It's, took me an hour to talk about, but it's really seconds to do. But when you understand what you're doing, you realize how much information this can give you. Okay. So that's one of the things we have due this Friday. In fact, I think that's the only thing we have due this Friday. Yeah. Now, I want you guys to do this test on your cars and get some results, and send me the recordings, and think about, like, did it match up with what I just told you, how it's supposed to work and what it's supposed to match up with, right? Use that as your known standard. I'm kind of making the assumption that you guys don't have anything wrong with your cars at that point. Where are we going with this thing next week? Well, next week, we have this thing on the horn, and we'll get into that. Next week, we have this video clip here for you to look at. And it, basically, I've done these tests on our RX-7 race car here. And I think I showed you guys this last week. And what you'll see is through this thing, I'm going to ask you some questions. So you'll see the meter, and then you'll see the question. What is the available voltage while cranking? Does this pass the test? And you see, okay, look at that. It went down to 11. I actually cranked it for quite a while. So it went down to what? Maybe just under 11. I think I saw a 10.97 there. Yep, 10.95. So then you ask yourself, okay, well, what was the state of charge? What was the available voltage right cranking? Oh, it was 10.95. Is that above 10.5? Yeah, it is. Does it sound like it was cranking over pretty good? I'll let you guys decide on that one, right? So you watch the video, the questions pop up on the video, but I also have the questions for you to answer right here. And you can just copy these questions and then paste it, and then paste it with your responses there. So it's kind of fun. It gives you a car. I couldn't give you a bugged car. So this is a way for me to show you something that has a problem and have you guys diagnose it. So in the video, I don't tell you what's wrong. You guys ultimately have to look at stuff and decide what's wrong. What's your diagnosis? What do you recommend we do at this point? And so then we'll, that's where we're going with stuff next week. So that'll give you guys a little bit of time. And what you might want to do is do this test on, if you got access to more than one car at home, do it on a couple of cars so you get used to how it normally works, especially on a car that's working correctly. And then you can attack that that video clip and see what you think. Okay, so very good. Now I notice, Tom, you said you had a question. What's your question, sir? You can turn your mic on and ask it, or you can put it in the chat. But I want to make sure I don't miss your question. See if you're still there. Yeah, Tom, if you got your question, remember, anyways, remember that you should be able to turn on your microphone and ask your question, or again, you could type it in the chat. So I'll keep going, but if you think about what your question was, make sure you let me know, and I'll be watching for that notation on our little chat window here. So if you have a question, maybe I could have already answered it, but anyways, I want to make sure that I answer it properly. Okay. So what I wanted to do was then go back to our modules and kind of see, well, where are we at this point? We know we're doing some charging system stuff. You know, I do want to show you some of my charging system presentation. And then we're going to look at maybe some of these advanced meter features, and then go into a case study tonight with a little bit of the time that we have left. Okay. So, you know, I felt like we did a pretty good job with CDX there looking at that charging system, but let me change my screen share here, and we are going to jump over to my charging diagnostics here and just look at some more of these components here. Just, you know, a little bit different than just looking at that animation. Okay, so I'm gonna make that full screen. I will then share that screen so you guys can see it a little bit better. So there's an alternator cutaway in blue here. You can see the rotor and those little like triangular pieces. Those become the north and south poles. You can look in here and you can see the copper windings of the rotor field winding on the inside. You can see the stator windings on the outside. That's where the power gets generated. And remember that it uses a couple slip rings and brushes to get the power in and out of this rotor. So just like a starter will eventually wear out its brushes, a high mileage alternator with 180,000 miles on it or something, at that point, again, the brushes will get to the point where they're worn out and it has to be replaced. Okay. So, you know, back in the day when we would rebuild things like alternators, one of the things you'd always do is put in some new brushes. You'd polish up the slip rings on the rotor. Those were some of the things that you did. A lot of times we just throw in a new voltage regulator, that type of stuff. So now one thing I guess I didn't make clear, and I do want to give you some other ways that you could use your meter, is an alternator. Why we call it an alternator is because on the inside here, when it generates power, it actually generates AC power or AC current flow. Okay. So alternating current, that's what gets generated in these windings here. Well, we know that our car, it's a DC animal. Why? Because it's got a battery, right? Batteries are DC. They're not going to want this AC. So what that means is we have to not only have a voltage regulator to make sure the voltage doesn't get too high, but we have to have, let me change colors here. We have to have a rectifier. So I have rectifying bridge diodes. Those are on the back half here. We have to change the AC. This is a Thomas Edison term. We have to rectify it to DC. before we ship it out of the back of the alternator and ship it over to our battery. So let's look at that. So in this picture right here, if I get rid of the scribbles, what you'll see here is a couple of things here. I'm going to put in green. These are my brushes right here. So you can see the brushes and they're right on top of those springs there. This black thing right here, this is your voltage regulator. So you can see that he's hooked to the brushes. How does he regulate the voltage? He controls how much power from the battery goes in through the brushes into the rotor, which is your magnetic field. And that controls how strong the magnetic field is, which will control how much power is going to be generated on the stator windings that surround that rotor. Okay. So that's all fine and dandy, but what about this DC to AC thing? Well, or I should say AC to DC. This black thing right here, these are your diodes. This is your rectifier bridge, and that there's 6 diodes in here that convert the AC voltage that's going like this, that convert it to DC voltage that's going basically like this. It's still pulsating. It still has a little bit of electrical noise, but for the most part, it's all positive. And there's 3 different windings in here. It's all positive and all overlaps. And what I end up with is, you know, with a little bit of noise on it, that 13.8, well, I'll change that color. That's hard to see. That 13.8 volts to our 14.8 volts, right? So I take the AC that's generated in the stator windings of the alternator directly, send it through the rectifier, which is a set of 6 diodes. Now the symbol for a diode looks like a little arrow with a line next to it. And what a diode is, it's a one-way electrical check valve. It allows current to flow in one direction, but not in the other direction, okay? So it allows it to go this way, but when it would try to go in the other direction, it stops it. And we use 6 of them to what we call full wave rectification, where we're taking the bottom humps and we're flipping them up to the top. So pretty ingenious how it works. So what I'm getting to though with this is that we have to take AC and convert it to DC. All right? We have to take AC and convert it to DC. And so what you see from this diagram here, a little bit more detailed here, guys. What you see here is that here's our stator windings. And notice that there's the 3 windings. They're wound up in a Y configuration. See how it looks like the letter Y here? They can also be wound up in a delta configuration. So a delta would look like that, that, and that. And there's advantages, disadvantages to each one. But the stator windings feed out and they go to these 6 diodes here. And that's where we convert it from AC. So inside these stator windings, what am I making? I'm making AC. Once it leaves the stator windings and comes out the big charge wire, going over here to the battery. At this point, it's DC, okay? Well, one of the things that can fail on an alternator is that, you know, 1 or 2 of these diodes, they could burn up, right? They could fail. So let's say I had a couple diodes fail. What do you think that's going to do to the power coming out of this alternator? Is it going to make more power? Is it going to make less power? Is it going to, what do you guys think? What do you think there? And I notice I got my question back on the chat. Yes, we can do older discussions as well. And I'll get to that in a second. What do you think that would do to the power being generated coming out of this thing? Well, let's see. Less power. You are right. You're going to have slightly less power, but here's the big thing. It's kind of a trick question. I'm messing with you guys. Remember, the job of the diodes is to convert the AC to DC. Well, guess what? It's not going to do as good of a job converting that AC to DC. So I'm going to end up with a little bit of AC ripple or noise on my alternator output. So here's another kind of advanced test you can do aimed with just a meter. Even this Harbor Freight meter could do it, okay? Here is what you would do is, let me erase some of this stuff here. And I would find that charge wire, and I like to do this right on the back of the alternators where I'm going to get my truest reading, okay? So the charge wire coming off the back of the alternator, that's going to be the biggest, thickest wire coming off the back of that thing that ultimately leads back to the battery, okay? So I'm going to find that big charge wire coming off the back of the alternator. This one has a B next to it, okay? And I would take my meter. I'm going to draw this green meter like our, where is it? Our performance tool meter or whatever. And I would take the positive lead of that thing and I would hook the positive lead right to this charge wire here. So I'm going to set the meter itself, I'm going to set its reading to AC volts. Let me make that a little bit darker color here. I'm going to set it to AC volts, which is going to have like the little sine wave next to it. So I set him to volts AC. I'm going to go to the 2-volt scale on this meter, a low voltage scale, and I'm going to take the positive lead of my meter and I'm going to hook them right to the back of the alternator. Then I'll take that negative lead. You know what I'll do is I'm going to hook them right to the metal case of the alternator, somewhere where it's not going to get caught in the fan or anything like that, but I'll hook them straight to the back of the alternator, because essentially, like, the body of the alternator is ground and that battery terminal off the back of the alternator where the biggest, thickest cable comes out, that's going to be the positive, right? So now I've hooked my meter directly to the alternator, so I'll get more raw readings. I've set them to AC volts, and now I'm going to force the alternator to work a little bit, okay? So at this point, I'm going to do a couple things. I'm going to, and let me change this color. I'm going to rev it up a little bit. So I'm going to put 2000 RPM, and I'm going to put a little load on there. I'm going to turn the headlights on. What should happen if I turn the headlights on, the battery voltage would drop, the voltage regulator, right? He would see that and go, oh, crud, I got to charge up this battery because these headlights are on. And so it's going to force the alternator to work a little bit. I'm not going to force it to work super hard, but I am going to force it to work so that I should have some amps pumping out of the stator windings, forcing through those diodes. If the diodes are doing their job, the power should come out and it should be DC. But if I had a couple burned out diodes, what I'm going to get is some AC noise. So what am I looking for here? I'm looking for the AC volts that I measured to be less than 0.5 volts or less than a half a volt AC. If I measure more than a half a volt AC, then I have diodes start to take a nosedive off of my alternator. And that's another test that I can do to see the health of my alternator armed with just my meter, okay? So what would you get in that scenario? You might have, the battery of the car doesn't really go dead, but maybe the car has weird drivability issues because it's getting this electrical noise. Maybe the alternator seems to make like a weird humming noise. Or maybe when you run a lot of your accessories, it just doesn't keep the battery charged like it should. That would be another test you could do of your alternator to determine the health of it based on like what's going on with the diodes in it. And all you needed to do was take your meter, hook them up a little bit different way, and now look for some AC voltage, okay? So we, so hopefully that makes sense to you, and you got to see some other parts. So like there would be my charge wire coming off the back of that alternator. And, of course, with alternators, the belt is super important, right? If the belt's slipping due to a bad tensioner or something like that, it's going to affect its output, right? So I find a lot of times people replace the belt and they overlook replacing the tensioner. And a lot of times the tensioner, especially if it's a high mileage car, the tensioner will likely need to be replaced. There's stuff that you can do with the VAT40 where you can actually measure its output. So if it's rated at 100 amps, I could test to see if it's actually making 100 amps. I could also do the same thing if I had one of my inductive amp clamps. But if all I have is a meter without an amp clamp, I'm a little bit more limited on what I can do. So I can measure voltage regulation, and I can measure for AC noise, and I can do voltage drops going back and forth to the alternator, but I'm really limited. So all right, so let me change that screen share back to the computer. So a couple things came up in the chat, and let me turn my chat window back on here. Some folks were asking about older discussions. We can certainly do older discussions. What I wasn't clear on is, do you have a question on one of our older topics or subjects, or are we talking about the discussions that are in our class, right? You certainly can do older discussions in the class, and even though they're due, they shouldn't lock you out. So like, this one, testing the relay, is still open for a couple more days. The one on the RX-7, that'll be open till pretty much the end of the semester. The only one that did close out was the one on the auto industry one. But if you guys want, I can open that one back up for you as well. But maybe you were asking about.
No, you just hit it.
Okay.
For me, you just hit it. I just had some input on electric vehicles because where I live, they have an electric vehicle. And the first one, the young man goes to school in Santa Clara, and it was a Chevy Volt, and the battery just was inadequate. So he'd get to Tracy and have to pull over and charge up for an hour. And so now he's got, oh no, it was a BMW.
Was it now he's got or a Volt? BOLT?
No, it was
VOLT.
No, actually, I'm sorry. The first one was a BMW, and that's the one that wouldn't make it. And now he has that Chevy, and he can go. He's graduated, but he can go all the way from Santa Clara to here on one charge. And then we went skiing one time, and let me tell you, you better charge up before you go because it's getting colder.
Yep.
And so you don't have the juice. And I'm thinking, so my input was that. I don't think it's when Governor Newsom says, blah, blah, blah. Okay, we have too much heat. We have too many fires. There's too many blackouts, and we've got too much elevation and cold. I just don't think it would work.
Yeah,
that's all
I was actually talking to somebody who used to be pretty high up in the Bureau of Automotive Repair and the Air Resources Board this afternoon. And he would agree with you. He said, like, that's realistically not going to happen. But you know what? It's going to force us to at least start moving that direction and pump out some more electric vehicles and get some more momentum behind the thing. So, as we get closer to that date, I'm sure there's going to be a lot of compromises. Now, there could be a big development in battery technology, right? Like if you could get a battery that could give you, 300 or 400 miles of range, man, it might be game over for the gas car. That, like, if you could get something that had really good range or that charged really fast, that would change stuff a lot.
Is that an ion battery, maybe?
Lithium ion right now is the current standard of where we're at. And, it's pretty decent as far as batteries go. It's about the highest energy densities we have. but you know, it's expensive and you need a lot of them. And you know, I mean, there's definitely challenges with it. That being said, there are people like with Teslas that they have a battery pack that can go 200, 300 miles. Tesla has a pretty good charging system infrastructure with superchargers, so they can go and do half-hour pit stops and recharge their battery and get 80%. And they can go from LA to Sacramento and do that with, you know, not as easy as you could in a gas car, but with, you know, minor inconvenience, they can make it happen. So stuff has come a long ways, but there's probably a long ways for it to go. But I think this will get changed as time goes on, but it's certainly going to get the ball rolling. And we've already seen electric vehicles advance a lot in their range. Like the first uh, groupings of them, like the Chevy, well, the Volt was really a hybrid type car where, you know, it had a backup gas engine. But let's say like the Nissan Leaf, the first generation Nissan Leaf, you know, you were supposed to be able to go like 80 miles. Well, realistically, you could, you know, if it was really cold outside and you're running the heater, or it's really hot and you're running the AC, maybe you're going 60 miles, right? So you were really limited. And I've driven one of those, and you were always thinking about how far could you go? Like, what was your range, right? When you have a car that can go 200-300 miles, it's a different story unless you're doing that skiing trip, that long distance trip. Then you got to plan it out. So um you know, I think for some things though, like fleets where they have a driver and they know what that driver's route's going to be every day, um you know, that's probably the hot setup, because they can, you know, plug that thing in at night and it charges up and it does the route the next day, you know. So there is definitely a lot of applications for it. It'll be interesting to see where it goes. I think that you guys, no matter what, will you know, have to learn how to deal with high voltage electrical systems and deal with high voltage safety. And so one of the classes I'm trying to get put on the fall schedule, and now I got to call another instructor. But one of the classes I'm looking to put on the schedule is our hybrid class, because I think, you know, the demand will be there for it. And I just think it'll end up being a necessary skill for you guys, is how do I deal with high voltage electrical systems? And, you know, what you would learn on a second generation Prius as far as dealing with the high voltage systems and the battery and the contactor relays and just the way the vehicle works, that can be applied to a Tesla, or just all kinds of different things, because, you know, high voltage safety is high voltage safety. All these things use similar components as far as contactor relays and the way the systems are broken down. So anyways, I'm trying to get that class added into our fall schedule. So good deal. With that, I think that kind of catches us up. We know what we got to do, right? Our assignment is to do those charging starting system tests where we're doing state of charge, available voltage, and then our voltage regulation. And really, it's only seconds to do, but it tells you a lot of information when you understand what you're looking for there. Okay. Um, from here, we're gonna switch gears in our class and move away from charging and starting, and we're gonna go to some chassis diagnostics and a few case studies where we can look at different ways where we can use our meter to diagnose what's going on with the car, and just to kind of show you different ways that you guys can do different testing with your meter. And really, if you're armed with a meter and you have understanding of electrical systems and you can read a wiring diagram, man, you can do all kinds of diagnostics. And so that's going to be kind of more of our focus. I got stuff that ranges from, you know, check engine lights to no starts. And we're going to be looking at, again, kind of going back to relay tests, but this time testing the relays on the car and doing some other things. So that's where we'll be moving to in next week and the week after that, as we kind of wind down a lot of our information. Where we'll finish things up is then focusing on the Snap-on meter. And for those of you that want to get Snap-on certified on this meter, you can do that. And it'll show you, you know, like what can you do, you know, what's going to be different between, you know, the $40 meter and the $400 meter. And it'll at least, you know, give you a nice little certification. It'll teach you more about meters and electrical in general, but it'll kind of let you evaluate, like, you know, is that worth it to me? Or those extra features like the min max and the some of the other features, are they worth it for me for that additional price? So but for tonight, that's all I had for this class, because we're going to switch gears and we're going to switch into our scan tool class. So for you guys that are just in the multimeter class, the 181 class, you guys are free to go. Okay. Unless anybody has any more questions that are specifically related to multimeters, I'll let you guys off the hook and we'll end that out.